And if you'd like to see more data and want to get snowed by the math, that also is an option. I'm happy to provide that after the talk. So what I'm going to be talking about are some problems involved with small satellites. And on a few of those problems, I'm going to describe some of the solutions that I've come up with and seem to be very practical in terms of dealing with some of those big issues. So to start, let me define for you what I mean by a small satellite. Usually in the literature, a small satellite is defined based on mass, which is a very good way of doing it. I'm going to be defining small satellite based on a side of an edge, and you'll see why that's relevant in just a minute. Obviously, given the fact that mass goes with volume, the two are intimately related. These small satellites, which are typically much smaller than a meter on a given edge in a form factor, are usually, but not always, low Earth orbit. That is to say, the orbital timescale is less or on the order of 128 minutes, and usually their orbits are somewhat eccentric, and typical average heights are 500 kilometers or so. Small sats in general, not always, have a short lifetime. And of course, they're satellites, so they have to have an RF base. And the fact that they have an RF base for communications and sensing and so on is the basis for having this talk to start in the first place. So what I've done below here is I've listed several dates and several small sats that are really kind of important in terms of this talk in particular. First of all, does anyone know about Fritz Zwicky and his artificial meteors? Anybody in the room? Oh, you've got to hear this story. This is worth 30 seconds. So Fritz Zwicky was a chemist and astronomer at Caltech, and he also was one of the pioneers in propulsion for solid rockets. He worked at the Aerojet company and worked in the Aerobee rockets. He actually went over to Germany right after the end of the war and assessed the V2s and brought them over along with the Army. Fritz Zwicky in 1946 had a project that put a bunch of BBs in a capsule and a charge below them. And he was convinced that he could send these BBs into orbit, which of course would mean the very first orbit of anything that was man-made. Well, they actually launched one of these V2s. The V2 itself, of course, couldn't go fast enough to attain orbital velocity, but the charge didn't go off. So the Army thought this was a silly thing to do after it failed and kind of gave it up. But then in 1957, we had Sergei Korolev and his colleagues in Russia, Soviet Russia, launch Sputnik in October 1957. Suddenly, there was an incredible effort to try to do something, anything. And one of the things that the Army did is they did the project again to launch these BBs called artificial meteors into space. And in fact, a month after, you don't even hear about this, a month after the launch of Sputnik, the Army successfully launched BBs into space with a depth charge. Now, the reason that's interesting is if you want to look at Sputnik as the first artificial satellite, these artificial meteors or BBs ended up being the first artificial planets because their orbits actually orbited the sun. They didn't orbit the Earth. So why isn't that in your encyclopedia or in your lore of satellites? It's not your fault. It's just a matter of size. Probably if they weren't launching BBs, we'd be having a very different discussion. The next object that I think is relevant here in terms of small satellites is Vanguard 1. Now, Vanguard 1 is actually still up in space. It was about yay size. And the reason it's important is it was the first satellite that actually had solar cells on it. So there was an attempt to try to extend the lifetime of the battery. That's how they were ran at first, by charging it up with a trickle charge from solar cells. Now, that eventually failed. And of course, Vanguard has not been operational now for many, many decades. But it was the first case where you had a solar cell panel on a satellite. The next one that I like to list is Telstar 1, which I'm sure we've all heard about. Telstar 1 was a a limited success. It was launched in 1962 as a communication satellite by Bell Labs, and it died very quickly because of radiation from nuclear blasts killing the transistors. But while it was up there, it did some very important work and really went to town with using solar cells on what amounts to a spherical satellite. Next one I want to mention is Oscar. Oscar is a great example of looking at a small sat as a small sat and understanding it has its role, and it can piggyback, for example, in other missions and so on. And the other thing that I want to mention about Oscar, it was the first amateur satellite, not amateur radio satellite, the first amateur satellite. And I think people tend to forget that it's historical significance of that. It was the first non-military, non-commercial satellite. And the last thing I want to mention in the list is CUBESAT, which is 1998. CUBESAT is a program that's been very successful. It was started by NASA. And the idea is you launch a bunch of these really tiny small satellites that are basically cubes and 10 centimeters by 10 centimeters by 10 centimeters as a cube. So people now talk about CubeSats being 1U, mean 1 unit, 10 by 10 by 10, or half a U or 3U and so on. They kind of look at describing these smaller satellites as being Lego-like relative to this defined 1U CubeSat structure. And it's really the nature of CubeSats that's brought to bear this notion of small sats being important. All right, well, here's the main advantage of small sats, and especially things like CubeSats: gravity rules. And that means that the less weight and volume you do for any given satellite, the easier it is to make, the time to launch is shorter, and the launch costs are much lower. It's a bit of a simplistic way of looking at, but if you look at how much it costs to launch a satellite relative to one side of the form factor of the satellite, it goes as that edge to the 4.5 or to the 6th power. So the cost of launch goes up dramatically, even if you double the size of the satellite. So costs are expensive if you make a big satellite. Fabrication costs are expensive. The time to launch is long and so on. So there's all kinds of reasons to make much smaller satellites. The cons, the disadvantage of having a smaller satellite, and when I small, I mean, again, less than 1 meter on an edge, is oftentimes you can't do very much with them. There's not a lot of different modalities of them. They tend to be RF feeble, meaning the ERPs tend to be low, mainly because they're small. They tend to have short lifetimes. Propulsion and control are big issues. I can discuss that offline if you want. There's all kinds of neat, clever ways to fix that. One of the cons, at least it's being considered a disadvantage, is there's going to be thousands of them over the next few years, and I'm going to deal with one of the aspects of that. They have very limited ability to power harvest, that is to say, mostly getting radiation from the sun. And they also have a low radar cross-section, which means if you want to ping them and make sure you know where they are, or whether they're still up there, or whether they're falling down, or whether they're trying to be hidden, they have a rather low radar cross-section. So they're very hard to find, even with large radar systems. Okay, so I'd like to summarize the 3 problems that I'm going to pursue in these 4 bullet points. One is that the RF link budget, it tends to be low with them because they have a small size and they don't have large high gain antennas. Plus, they don't have a lot of ability to store power because they don't have a lot of solar cell area, and usually they don't have a lot of weight devoted to battery or storage. Again, they're hard to detect with radar because they are physically smaller. Less solar cells means less ability to power harvesting. And the last one I want to mention is what I call smudging the sky, which is to say, when you have many of these satellites, especially thousands, you don't have to wait long to see a satellite going in front of you. And that becomes a problem, particularly if you're an astronomer. And I think there's a fun solution to that, but I'm at this point, I'm really listing it as a problem. Okay, so I need to take you into a paradigm shift here. And now it's going to sound kind of obvious. Do me a favor, hold up your smartphone if you got it near you. Okay, so the front of that smartphone accomplishes many things. It has a camera, it has a display, it has a touch screen, all kinds of stuff. It's a multifunctional, to point out Dr. Latakia's talk, it's a multifunctional surface. That idea has origins somewhere, and I'm going to show you where some of those origins came from. But right now, I want you to understand that what you're taking for granted on a touchscreen TV or your tablet or computer or your smartphone or whatever is that the surface is important for functionality. It isn't necessarily where you place the sensors. It's the fact that you're sharing that surface area for those sensors. Now, on satellites, for a very long time, the notion was that the platforms, they were platforms for sensors. You put an antenna here, you put a solar cell here, you put a temperature sensor here, you put another sensor here. Neither the twain shall meet. That is a paradigm that's shifted and needs to shift. The fact is that satellites need to be looked at as surfaces that have sensors and share that surface with the sensors. You don't separate things out anymore. You combine them, you do layering. You'll see what I'm talking about in a minute. So let me give you an example. This handsome gent here is me just a few years ago. And what I'm holding is Sputnik, not Sputnik. Sputnik doesn't exist anymore, but Sputnik does. My little potato spacecraft here is about a third the size of the original Sputnik. I actually use it as a phantom, that is a calibration source for doing radar measurements. But one thing, obviously, I want to point out is that, you know, you got the antennas sticking out, and that's it. The rest of it is this globe, and there's all kinds of guts inside, but there's nothing on this surface. The only surface that's being used, per se, is for the antennas. By the way, there's a reason why it looks so cool. This idea of having the swept back antennas and the BB in front, that wasn't, how shall I put it, a Museum of Modern Art design incentive. That was designed because the antenna went on the very top of the nose cone of the rocket, and the antennas were conformal to the nose cone. So the reason they were swept back is they were lying up against the nose cone. And then when they wanted to show it up and send it up into space, once it got high enough, they pushed a switch and a spring went boing and pushed the whole thing out. So it looks that way because it was a kludge method and an easy way to get it up in space. All right, my point is that the surface of that satellite is really non-functional. What does it do? It doesn't do anything. But the fact is, it is the surface, and that ends up being the most important parameter to consider. You know, we have a bad habit of assigning functions, as I said, to different surface regions, but we don't look at the surface as always being multifunctional. Now that's changed, but let's go there. Anyway, the paradigm shift is that we went to layered integration. That's what your cell phone is. That's what your tablet is. You open up your tablet, you're going to see not only the screen, you're going to see this battery and CPU and all kinds of other cool things. Layer, 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 layer. It's the basis for all modern devices. And it's the surface that's the tool here. Now, when you include the notion of power harvesting, power gathering, then you get something that's I coined an aperture engine, which I also call the divine sandwich. So an aperture engine is a surface that converts a form of energy or information into another with layers or grids of energy for harvesting, sensors, converting, and storage. Now, what gives me the right to define this? Well, I'm not saying I invented the cell phone. I didn't invent the cell phone. Marty Cooper invented the cell phone. But the idea of having this layer system, especially for gathering power and having everything underneath it, I came up with in 1972. Science fiction. I first published it in 1998, submitted satellite patents in 2010, and now I'm going to give you a little bit of historical perspective. This is the paper that I published on it in 1998 on SETI, the search for extraterrestrial intelligence. What I was trying to point out is that if you take a given area and define that as an area for gathering power and an antenna for transmitting out, you're making the most efficient use of a surface you have. It's silly to separate everything out. And if you do that, what happens is you increase the area of the surface. The amount of power you gather goes as the area, r squared. For example, on the Earth, you have about, I think it's 1395 watts per square meter in the best case scenario for gathering power. But the gain of the antenna also goes as the area. So that means that if you combine the area of the power gathering with the antenna itself, you end up getting a power increase going as the side to the fourth power, or to the area squared. It goes as r to the fourth. It goes up dramatically. And what I did is I did some back of the envelope calculations saying if you do this as a sandwich where the antenna is in the top and the solar cells are below, and then you have these layers. Again, this is pre, iPhone, layers of other things. You can construct what I call this aperture engine for SETI, the size of a football field, and someone can easily detect you from an Arecibo on Earth. In other words, you probably have interstellar hams who've done this, who are taking things the size of a football field and transmitting all over the place and wondering why we're not picking it up. The entry barrier to being able to do this is low. It doesn't take a lot of surface area in order to have enough ERP transmitted to get across the galaxy and have it detected. So here on the right, I just blew up one of the, come on, baby. Blew up one of the diagrams. What I'm saying is that if you have one of the sandwich layers for collecting power, and then below that you have a transmit module, and above that, you have an antenna, and combine it, you have this sandwich, which will transmit as a surface with r to the fourth. By the way, when I did the r to the fourth, no one believed me, and I said, well, do the numbers. I mean, combine it, you can see that as well as anyone else. It was unexpected. So that was 1998. That was a ground-based system, and certainly we could have done this ourselves rather than expecting ETs to do it. But now we're in 2022, and this is an aperture engine. Anyone know what this is? RC, I bet you know what that is. No? Okay, that's all right. It's called Blue Walker 3. It's a shakedown satellite done by AST Mobile, who went up a few months ago. Not at all clear if it's working, by the way. But, what you're seeing is the white stuff is a layer of dielectric resonator antennas. And then, of course, they have the transmit stuff as layers in between, all that good things. Then the backside is the solar cells. So this is indeed an aperture engine on a satellite. It's in space. So what this teenager in his boring physics class thought up in 1972 has now been realized as a spacecraft 50 years later. Now, I'm not the only one to think about these ideas. I'm really trying to give you the origin and, a little bit of a historical perspective, especially on, the original paper from 25 years ago. All right, so let's talk about aperture engines. The point is that if you really want to use a small satellite, every single millimeter of space has to be used constructively to gather power, to be sensor, to do what you want it to do as a satellite. There's no exclusive area devoted for anything. The antenna ERP, it turns out, for some of these very small satellites, say CubeSat size, is actually pretty moderate. And in this case, you solve the RF feeble problem by taking advantage of the entire surface being able to be used as part of the antenna. At the same time, it's being used to gather power harvesting from the sun. By the way, when I first did this, everyone said you can't do it. They said as soon as you put an antenna on top of the solar cells, it's going to stop working. It's going to have transmission line effect. I said, yeah, I know what it should do, but I'm going to do it anyway because I'm not being funded by a grant and I want to see what happens. So I did the layering, and it so happens that at S-band at about, about a third of an inch, quarter of an inch, very, very close spacing from the solar cells acted like a very good back ground plane. I didn't have a lot of transmission line effect, and the antennas worked pretty well. Of course, it depended on what kind of antenna you used. But if you looked at the antenna as a layer on top of the solar cells. It worked, and it worked very well. So what I'm saying is that you actually can solve that problem. Give you the numbers, then I'll go back to this one. Whoop. I actually put numbers here. Here they are. So let's say you take a small CubeSat, which is about, roughly 8 by 8 by 8 centimeters. You can gather very conservatively 5 to 8 watts. By the way, it's a myth that you don't get power on the sides that are pointed towards the Earth. The Earth reflects roughly about a third of the sunlight that it receives back at the satellite. So you're not wasting yourself by trying to get power by reflection from the Earth. Let's assume a low duty cycle on transmit, and that you're able to store with this trickle charge, so you can easily put out 20 watts. You don't want it to be on all the time, but 20 watts is realistic. You can get an S-band antenna, even on a small form factor like that. You can super gain and get 10 dB of gain. So your total ERP is 200 watts. 200 watts at 500 kilometers, I'll take that any day. That's very easily detected. So the point is, if you really change the perspective of how you do this, you're going to find out your restrictions are less than what you assumed. Now, let me just show this diagram. This is a histogram showing the percent of surface area being used for solar collection. That's the blacks here, versus the amount taken up by the antenna. And of course, this is all normalized to the total surface area of that given satellite. So you can see very little percentage of Vanguard 1 was devoted in surface to collecting sunlight, and very little was devoted to the antenna. More so on Telstar 1. When you get to Blue Walker 3, which is that monolithic one that I showed you, that's only half and half. You're not using the white side, for example, to gather power. So that's about 50%. My point is that if you take advantage of this efficiency, you can get roughly 90 to 95% of the entire surface to being devoted to gathering power, and 90 to 95% being devoted to the antenna. Efficiency helps. All right, this is a picture of a section of an aperture engine. In the back, what you're seeing are, in the dark blue, are solar cells. On top of that, a few millimeters away, you're seeing a transparent substrate with a fractal antenna on top of it. And this goes on top of the solar cells. It cuts down the power by about 5 to 7%. Very little power is lost by putting this on top. And in fact, I'll show you where that goes in just a second. But the point is, this works. It was tested. I actually built a prototype many years ago, so I wasn't surprised when other people started getting interested in putting up aperture engines and looking at the problem independently. All right, so now I'm going to extend the idea of aperture engine, not just to, can we get beyond the RF feeble problem, but can we also deal with the notion of using it as a tag, as a license plate on a satellite? So if you have a satellite that's this tiny or even smaller than that, it's very difficult to be able to track that orbit continuously from a ground-based S-band system. S-band is the frequency where you usually are looking to find out what's up there. So the way this is usually dealt with is they make something called Van Atta arrays, which would be too big on these small satellites. Or you do a transponder that is a powered transmitter, and you stick it on there, and it beeps away and beeps away. And, that way you can try to pick up and find out the ephemeris of the satellite. You don't have to do that. What you really need to do is increase the radar cross-section of the small satellite. So how do you do that? I'm going to show you. What you do is you put some metamaterial on top of the solar cells and the antenna, and it's translucent, reasonably transparent. Here's a layer. That's my room number. And what you do is you increase dramatically the radar cross-section in dB of that small satellite. So now you have something that looks much bigger than what it really is. Now, what I'm going to show you is data from this baby here. This is a small form factor size for a half a U CubeSat. So this is 5 centimeters by 5 centimeters by 5 centimeters. And what I did is I put one of these two of these layers on here, one and then two of these layers, and then measured the radar cross-section. I should say the reflectivity specifically to see how it would change. So again, some of these are often called metasurfaces because they're obviously surfaces. Here are the results. So I took it at 3 frequencies all around S-band and with 1 or 2 layers and with the solar cells alone. So if you measure the reflectivity relative to just say a piece of copper, you end up you end up with the solar cells actually being about 0, maybe a little bit more enhanced than just the copper back there at 5 centimeters by 5 centimeters. But if you add these layers, these metasurfaces, and yes, they happen to be fractal. I had to put that in the talk. You end up getting a fair increase at some of these frequencies. For example, at 2.5 gigahertz, can I press the right button? That's the real question. You end up with about 5.5 dB increase in the reflectivity. At 3.3, you end at 4.5 dB. Now, we've done the experiments and we can get 10 dB. We can even get 15 dB. The problem is, like any other set of gain systems, you end up being too directional. So the trade-off if you go for too much gain is you end up being too narrow a beam, which is not good if your satellite is going beyond or rotating and so on. So the point is you can increase this reflectivity using a metasurface on top of solar cells or on top of the aperture engine, which is a little more sophisticated than just the solar cells, with virtually no penalty to really speak of. It doesn't add a lot of weight. You don't lose a lot of power going to the solar cells, and you don't have to use a transponder. So we get that guy out of the way. Now you know where things are. All right, let's go to the next one here. By the way, there is a physical mechanism for this. It's called superscattering. And if you want to go to the literature and hear about excitation of quadrupole moments and so on, that's fine. I'm with you on that, but I'm more interested in how do you make the practical system work? And it turns out by guided trial and error, you can learn a heck of a lot about the system without necessarily needing to go to a sophisticated simulation before you go and test it. So the mechanism is called superscattering. That's not a term I came up with. And the belief is that you're enhancing the radiation through excitation of a quadrupole moment. All right, last thing I'm going to talk about is, excuse me while I smudge the sky. Now, we all know about Starlink. Ah, you did get the reference, good. Starlink is a wonderful system. I don't know if you've seen Dishy. How many have seen Dishy, the little dish that goes with it? It's tiny. Nice. They did a really nice job on that antenna, not one of mine. And the problem is there's a lot of Starlinks up there. And if you wait a few minutes, you're going to see a Starlink on a clear night. And then you're going to see another one. And then you're going to see another one. The problem is that when you suddenly get a lot more satellites up in the sky, it's going to be like contrails above Logan Airport. You're going to constantly see things happening and so on. This does not make some astronomers happy. And this is an example of what I'm talking about. This is a time exposure done by an amateur of the Horsehead Nebula in Orion. And those streaks are trails of satellites that go through over the course of time. So it turns out this has become a huge activist and political hot button. And there are efforts in the astronomical community to try to stop these thousands of satellites from going up. And I'm an astronomer, but I'm not an activist. So I like to solve problems rather than tell people how they should be thinking about them. So I'm going to give you a real easy potential solution. And what I call it is happy trails. We're going to be doing happy trails because you're not going to see them while you're doing your astronomical observation. And before I go into a very simple way of describing how to do that, let me just point this out to you, if I can get it to work. When an astronomer looks up in the sky, they don't look at the whole sky. They look at a very small section of it and sit for a while, try to get the sensitivity to detect the objects they're trying to look at. So they'll look at one place here, then they'll look at another place here, and another place there in the sky, another place there in the sky. So what typically happens is they have to trade off how long they're looking at a given position, a spot in the sky, field of view, versus how long it takes to move the telescope to a new one and so on. So it actually becomes an interesting optimization problem of, I want to get as much time on these 10 objects I want to look at, but I'm going to have to move the telescope around. How do I do that to optimize the dwell time on each one? It's an interesting problem. There are programs that help do that, but typically there's a huge trade-off, and you lose 30% from, thank you, you lose 30% from optimization. So the other problem now is you've got these star trails. So the star trails are going to be in, I'll get back to the mic in a second. They're going to be in your field of view. They're going to cross it every once in a while, even though there's one over here, one over here. So now your problem is not just how do you move the telescope and sit on the objects for as long as you want. It's how do you avoid the star trails? And that optimization is not easy. So I'm just going to very quickly show you. These are the 4 points that you need to do this. It ends up being a Lebesgue optimization problem, very interesting, and it's pretty easy to do. So there's a good chance that moving in the future, we will have these programs. You'll be able to avoid the star trails and get your observations as well. So I'm going to end it there and take a couple of quick questions. Thank you. Any questions? If you can. Julio, if you can do this. Thank you very much.
So in the piece of your talk where you were describing using the metamaterial as essentially a transponder, where a
passive transponder, yes.
Right. So what is happening there? Is the ground station illuminating it, and based on a pattern of reflection versus absorption, you get a pattern that you can, line up to a code, or is there some other process happening there?
That's basically it. What's happening is that it is a mirror and you're reflecting back, but because it's such a small mirror, normally it doesn't reflect very well and you may not be able to detect it. So the first objective of the metasurface is to increase that reflectivity so it has the apparent size of a much larger mirror. That's the first thing. The second thing, which you hit on, which is very important and I didn't mention, is that you can do a relationship of absorption versus reflection, and you can code that as a function of frequency. So you're right, you can say this, it's almost like a barcode. You can have the satellite saying at 2.5, I can see it, at 2.9, I can't, at 3.1, it's really bright again, and so on. And that signature with a metasurface can be unique to that satellite. Did that answer your question? Thank you. I didn't point that out. I appreciate that.
Thank you very much. We have one more question.
One more quick question.
For Dr. Cohen. Anyone?
Okay, thank you very much.
Thank you very much.